So I have a spring with K equals 1,000 newtons per meter. Okay, that's the spring constant. And it's compressed by 10 centimeters. And it's going to fire a 55 gram mass straight up into the air. Okay, and I want to know, how high does the mass go before it stops, in other words, its maximum height, and how fast is it moving when it's 3 meters above its original height. Okay, so it's actually going to go up to about 9 meters, and so it'll pass the 3 meter mark, and I want to know, when it passes the 3 meter mark, how fast is it going. Okay, just to show you a picture of what this looks like, here's a picture. Okay, and so here's the spring here, and this in red here, I'm trying to indicate that I've actually compressed the spring by 10 centimeters. Okay, and I've got this square box here, that's my 55 gram mass, and it's sitting on top of the spring, and it's kind of, the spring is loaded, compressed, and then I release the spring, and it's going to pop up into the air, and when it gets to its maximum height, of course, it stops. Okay, and it's also going to pass the 3 meter mark. Okay, now a few other things to notice here before I actually solve it. We can take h equals 0 right there. Okay, that's after the spring has been compressed. We can say that's h equals 0 for calculating gravitational potential energy. Okay, and at that point the velocity is 0. Okay, because like I've compressed the spring and I'm kind of holding it there. So is the box moving? No, I'm holding it there. Okay, so there's no velocity, and I'm also taking that as h equals 0. Okay, at this point right here, all the energy is going to be in the spring. Okay, now it's going to pop up, and then when it gets to its maximum height here, well, then the spring has released all its energy, so there's no energy in the spring. It comes to a halt again, the velocity is 0, so there's no kinetic energy, and all the energy is going to be into gravitational potential energy. Okay, when it's here at the 3 meter mark, okay, it's got a velocity, and it's at 3 meters, so it has a kinetic energy and has a gravitational potential energy, but the spring has sprung. The spring is completely uncompressed, because it's at 3 meters and the spring was only compressed 10 centimeters. And so there's no energy in the spring, but there's energy in both gravitational potential and in kinetic energy. Okay, so keep that in mind, and we'll solve the questions now. All right, so the first question was, how high does it go? How high does the spring, the mass, go before it comes back down? Well, you know that you're going to have to use energy, so let's calculate the energy, the total energy. And the total energy, you know, because you know it when the spring is compressed. Okay, you can start with this equation right here, which will work at every point in the dynamics. Okay, so what does this equation say? So I use the square brackets to indicate kinetic energy. So there's kinetic energy, and there's only one term to the kinetic energy. There's only one way to calculate kinetic energy. That's 1/2 mv squared. Okay, so that's kinetic energy, and then this square bracket here, that's your potential energy, and there's two contributions to potential energy: gravity and the spring. Okay, however, initially, when the spring is loaded down here, let me show you back on the diagram. Initially, right here, okay, let me do it in purple, like right there. Okay, when you're right there, there's no velocity and no height. Okay, and so initially the velocity is 0 and the height is 0. Well, if the velocity is 0, then the kinetic energy is 0. There it is. And if the height is 0, then the gravitational potential energy is 0. There it is. And all the energy is in there. Okay, so 1/2 K is 1,000 newtons per meter right there. Okay, because I tell you what it is. All right, and I've compressed the spring by 10 centimeters, converting it to MKS. That's 0.1 meters. There that is. Okay, and that works out to 5 joules. Okay, so we didn't answer the question yet because I asked how high does it go, but we're going to use conservation of energy. So there it is. It's 5 joules. Now we can use that energy here. So we know it's 5 joules down here, and that means that the energy up here is also 5 joules, the total energy. All right, so do it again. Do the same calculation again, like that. Okay, and when you do, though, now you're at the top. So at the top, the velocity is 0 again, And it started at 0, then it moved up, and then when it got to its maximum height, it stopped again, so it's 0 up there. The spring has uncompressed, so x is equal to 0 because x is the measure of the spring's compression. All of the energy is where? It's an mgh. Okay, so let's go ahead and substitute in what we have. Do we have E? Yeah, that's kind of the point. The whole point of doing this was to get that 5 joules. Okay, so now we know the energy up there is 5 joules. Okay, the kinetic energy up there is 0. Okay, mgh, for m we have 55 grams, but we got to put it in kilograms. Okay, so here I add 55 grams. To convert that to kilograms, divide by 1,000, so it's 0.055. So there's the mass in kilograms. G is 9.8, rounding it off to 10 as we always do. And then H, that's what we're trying to solve. How high does it go? Okay. And then there is the potential energy due to the spring, but the spring is uncompressed at this point, and so that's 0. Okay, and so that just reduces to this, and that tells us that it gets to a maximum height of 9.09 meters. Okay, so there you go. There's your maximum height, and it answers this question right here. How high does the mass go before it starts coming back down? All right, the last question, or second question, I guess, is how fast is the mass moving when it passes the 3-meter mark? Okay, well, it will definitely pass the 3-meter mark because it's going to go up to 9 meters. Let's go to the diagram again. And so now we're looking right here. Okay, we're looking right there. All right. And what can we say? Well, x is 0 there. I guess I didn't write it in here in blue, but x is 0 because it was only, the spring was only compressed 10 centimeters. So when it sprung, it went back to 0. So you're at 3 meters, which is bigger than 10 centimeters. So the spring is out of the picture. Okay. There is a velocity because it's still moving up. It hasn't reached the 9-meter mark. Okay, and the height is 3 meters. Okay, and so let's make use of that and calculate how fast it's moving at that point. All right, so here we go. All right, start from the same equation again. All right, I mean the form of the equation is the same, just the values of the numbers are going to be different at different points. Okay, so yeah, we still have kinetic energy and potential energy and 2 contributions to the potential energy, but now when h is equal to 1 meter, the velocity is whatever it is, I don't know. Okay, and x is equal to 0. All right, and so let's plug in. Do we know the total energy? Yeah, it's 5 joules everywhere. Okay, 1/2 mv squared. Well, we have a half. The mass 55 grams. That's 0.055 kilograms. V squared we don't know, but that's what we're trying to calculate. Okay. mgh, m is 0.055 grams. G 10. H is 3. Okay, 3 meters high. Plus the potential energy due to the spring, but the spring doesn't have any potential energy left. Okay, so that reduces to this. All right, and then just subtract 1.65 from both sides there. Divide by that number there, and then take the square root, and I found that the velocity is 11 meters per second. Okay, so when the mass passes on the way up, when it passes the 3-meter mark, it's going to be traveling at 11 meters per second. So it starts off at 0 when it's on the spring, and then the spring shoots up, and then it's got some velocity, it gets accelerated, and then as it goes up, it's actually going to slow down because the velocity, the kinetic energy, is going to become potential. When it gets back up to the very top, it's going to stop again. Okay, so it went from all potential energy in the spring to a mix of gravitational potential energy and kinetic energy, and then at the very top it's all gravitational potential energy. Okay, and that's how this problem gets solved. So I thought it was a little bit of a variation on, I usually do the roller coasters, with cars going downhill and uphill, and then there's springs involved and so on, and those are good problems too, but I just thought I'd show you that this could be applied to this other situation here, which is a little bit different than a roller coaster. Okay, so there we go. That's our energy problem. Let me see if there's any questions in the chat here. All right, well, we're going to do an oscillator problem, and then we're done. Okay, it'll be kind of a short class. But before we do, I did invite Physics 111 to, just, whoops. I lost the, it happens. There we go. I did invite Physics 111 to watch the energy problems because I didn't get a chance to do it for them. But what I have highlighted here is not for Physics 111. It's just I'm going to do just a very quick review of some of the calculus that related an oscillator to a spring. So if you're a physics 111 student, just don't look, okay? When we get to question 7, then you can start paying attention again, okay? So I just don't want to cause confusion because that's not part of your course at all right? So for physics 101, you know, we're talking about springs. I've got this potential energy for a spring, and we were talking about springs, and then suddenly I bring in oscillators, and you go, well, what's the relationship between springs and oscillators? Well, intuitively, I think you realize that if you put a mass on a spring and you know, compress the spring or stretch the spring and you let it go, it's going to oscillate back and forth. Well, that's intuitive, or, you know, qualitatively, but we could actually prove that springs cause simple harmonic oscillation, okay? And simple harmonic oscillation I introduced earlier in the course because I gave you this, okay, when we did the kinematics of oscillation, okay? Basically, oscillators, you know, they just do sinusoidal motion back and forth, okay? Either sine or cosine. I chose the cosine. It doesn't really matter. I don't even know why I chose cosine instead of sine, but I did, okay? And there it is. So what's the relationship? How can you go from a spring and prove that a spring pushing a mass back and forth will actually do simple harmonic motion? And this was the derivation that I showed you. You start from 3 things. First, you start from the fact that, you know, a spring, when you compress it or you stretch it, the amount of stretch or compression that you get is proportional to the amount of force that you apply. So, you know, if you apply like 1 Newton, it stretches this much. You apply 2 Newtons, it stretches twice as much. You apply 3 Newtons, it stretches 3 times as much. 4 Newtons, 4 times as much. In other words, the amount of stretch that you get is proportional to the force you apply, and vice versa. And that's this equation right here, okay? And this is also known as Hooke's law. I think next semester you'll do a lab on Hooke's law, okay? And F is equal to minus kx. The minus is just because if you push one way, the compression is the other way. Okay, if you push this way, I'm pushing that way. Well, then, you know, it wants to restore in the opposite direction. Okay, so that's what that negative sign is. All right, and K is a measure of the stiffness of the spring. Okay, and so you know, the stiffer, the harder it is to compress, right, the less compression, the less X you're going to get for the same amount of force. All right, so K is this spring constant. All right, that means that no matter what oscillator you have, whether it's the tiny little cilias in your ear or a skyscraper, anything that has some kind of rigidity has a K associated with it. You don't have to have a physical spring in there. Just like anything that's rigid has a K associated with it. Okay, great. So you have that equation. You also have Newton's second law, which is this equation. Okay, and this is the part that makes it non-physics 111 friendly. There's a relationship between the acceleration and the position, and it's the second derivative. The acceleration is the second derivative, okay? And so now, if we plug this into Newton's second law, and we plug this in for the acceleration, Newton's second law turns into this. I mean, it doesn't look like Newton's second law there, but it is. That's your F, right, from this, right? There's your F, is equal to M, and there's your A. Okay, and now let's divide both sides by negative K squared. I guess I could even put another line in here because you might wonder, geez, how did you get that? So over here I've got like minus M divided by K, like that. Oh, actually, I want to do it the other way around. I'm glad I did that, actually, because I noticed I made a mistake. This should actually be like this. Negative K divided by M, okay, multiplied by X. All right, I made a mistake there. Okay, and that means I should get rid of that and then move this to the other side there like that. Okay, good. Okay, I lost an X there. Okay, so what did I do here? Well, I divided both sides by M. Okay, so you can see here I had K and now I have K over M. So I have the second derivative of X is equal to minus K over M times X. And I'm going to rewrite that K over M. I'm going to call that omega squared. And that means that I get my first formula that's useful, which is omega is equal to the square root of K over M. Okay? And you say, well, what the heck do you do with this? Well, it turns out that if you take this and you differentiate it twice, right here, so that says take X and differentiate it twice, you get that. Okay, so what does this prove? This proves that if you have sinusoid, if you start off with a spring you get sinusoidal motion. Okay, and the way it proves it is that, there it is. There's the spring causing, acceleration, and you say, all right, well, what x could I use in there? And you could try a lot of different x's. You could try like polynomials and things like that. The only thing that's going to work to solve this, the only thing that says, look, if I differentiate it twice, I get the same thing back again, is a sine or a cosine, okay? And there it is. And the other thing is when you look at this and you say, what's the period of that? It's related to omega by that. And there's the second equation that's useful, okay? So this equation is useful for the angular frequency, and that equation is useful for the period. All right. By the way, this is going to become much more important next semester, so don't mind dump this over the break, okay? Because when we do, whoops, I lost it again. When we do waves, it'll come up again. All right, so Physics 111, you can start listening again, okay? So here we go. Here's our problem that we're going to solve, and then we're done, okay? So we make an oscillator with a mass of 3.5 kilograms and a spring constant of 15 newtons per meter. And so, attach this spring, attach this mass to the spring. And then, it wants to sit at equilibrium. My finger here is equilibrium. Mass wants to sit at equilibrium. I'm going to stretch it out 55 centimeters or 0.55 meters. Okay, so I displace the mass a distance of 0.55 meters, and then I release it from rest. Okay, so I pull it out here, and I don't push it. I just, it's there at 55 centimeters. I just let go, and it'll start to swing back and forth. Okay, so that's what we have. All right. So the first question is, what's the period of the motion? In other words, how long does it take to go back and forth once? And you take a look at this, and you go, geez, how would I answer that? It doesn't seem like I'm giving you enough stuff. Well, you don't answer it directly. There's the equation for the period. Whoops, it's being cut off. Okay. Well, let me just put it down here. Okay. So there's the equation for the period, but then you say, oh, well, I do have K and M, so I can get omega. Okay, so that's this equation right here. Okay, and all right, and so now it's just a matter of plugging in numbers. Let me just cut and paste that. All right, so omega right here is equal to the square root of K over M. All right, and for K I put in 15, and for M I put in 3.5, and that gives me a frequency of 2.0702, and the units are hertz. Okay, so then I didn't ask for the angular frequency, although I'll tell you right now, as soon as you've got a problem with simple harmonic, oscillators, you're going to be working with omega one way or another. It's hard to avoid it. Okay, so then the period here, that's going to equal 2 pi. So there's 2 times 3.14 divided by the frequency, and that gives a period of 3.03352 seconds. On a test, I would round that off to 3 significant figures. That's what we've been doing throughout the course. So t is going to be equal to 3.03 seconds. Okay, so I pull it out here, and this thing's going to go back and forth, and if I start it at this point, I start my stopwatch and I say, how long does it take to go there and back? A full cycle, 3 seconds, just a tiny bit over 3 seconds. Okay, next one, what's the amplitude of the motion? Okay, so I wouldn't say it's a trick question, but there's no calculation that you need. Basically, the amplitude is just the furthest displacement from equilibrium. Okay, and at that point, the velocity is 0. So, if equilibrium's here, if equilibrium's there, and I pull it out here, and I let go, it's going to go back and forth. What's the furthest it's going to get from equilibrium? Well, that's where V is equal to 0, and that's at the end point at the 55 centimeters. Okay, so there's really nothing to calculate. You say, well, how would I know that? Remember, wherever V is equal to 0, wherever the velocity is 0, that's the amplitude. Okay, that's going to be your maximum displacement. Think about it. Once it stops, it can't go further out. Okay, so wherever it stops, wherever its velocity is 0, that's its maximum displacement. Well, we released it from rest, so that's 0 velocity, and that means that's the maximum displacement, 0.55 centimeters. Okay, all right, so 0.55 meters, okay, or 55 centimeters. Okay, that answers that question. what's the maximum velocity? So there's actually two ways to do this. Um, One is using the kinematic equation that I gave you last uh, the first third of the course, okay? But let's do it using energy because that generalizes a little bit more, okay? So we'll do it both ways to show you that you can do it both ways, all right? And so first you're going to get the, here, I'll cut and paste the whole solution here. First, let's get the total energy. And so there's, oh, sorry, I highlighted too much. There's the equation for the total energy right there. There's the kinetic energy there, and there's the potential energy there. And the potential energy is only the potential energy due to the spring. Okay, there's no gravity in this. There's no MGH. Okay. So did I give you enough information? Well, yeah. V is equal to 0 when x is equal to a. Okay. So just remember, a is the amplitude. We could have called it x max. Except that every other textbook in the world calls it A. All other physics courses call it A. So for conventional reasons, we have to call it A. But you can think of it as X max. It's your maximum value of X, okay? And we just argued that that's going to be 0.55 meters, okay? But at that point, the velocity is 0. So when you plug into this, the kinetic energy is 0 here. And that one is equal to that, 0.5. K was 15, and A was 0.55 squared, and that gives you this energy there, which rounds off to 2.27 joules, okay? Now, that doesn't answer the question. That just tells you the total energy, but now we can use that to calculate the maximum velocity, okay? So at the endpoints, all the energy is potential because there's no velocity out here, so all the energy is potential. And this thing oscillates back and forth, back and forth. The endpoint, it's all potential. By the time it gets to the middle, to equilibrium, x is equal to 0. And when x is equal to 0, all the energy is kinetic. Okay, because x is equal to 0, so it's maximum velocity, all the energy is kinetic. And then back out here, it's all potential. So it goes all potential, all kinetic, all potential, all kinetic, all potential, like that. And then if it's like somewhere in between, it's not at the endpoint and it's not at equilibrium, then it's a mix, a little bit of kinetic and a little bit of potential. Okay, and so I have that equation right there, all right, which is kinetic plus potential. But we're at equilibrium, so at equilibrium, V is equal to V max, that's your maximum velocity, and x is equal to 0. So this time, your kinetic energy doesn't disappear, all right, but your potential energy does. Okay, and the energy here, well, we calculated that above, okay, and that's equal to this, all right, and that allows us to solve for V max, and we get that V max is equal to 1.44 meters per second, all right? So that's one way to answer it. In my previous class, someone said, well, I remember this equation here that you gave us way back when. In fact, I didn't give it to you. I actually derived it. V max is equal to omega A. It's totally correct. And it's, it's not different. Okay, it'll still work. And so I showed them that it would work. I just plugged in for omega here, and I plugged in for A, and sure enough, I get the exact same number. Okay, now this was that was obtained using kinematics, and this one was obtained using energy. But obviously, the two can't be in contradiction to one another. Now, the reason I did it this way is because this approach generalizes. Okay, this equation here will only work to equate the maximum x, in other words, A, and V max, so, okay? But in my next question, you would see that there's no equation that you can possibly use there except for a conservation of energy. So if you take a look here, all right, I asked the question, how fast is it going when it's 0.25 meters from equilibrium, okay? So its maximum is going to be 0.55, and now it's at 0.25. It's closer to equilibrium, so it has some velocity, and we wonder how much velocity does it have. Well, you certainly can't use this equation because it won't work there, but this one will, okay? That one will. Only now, it's not that V is equal to V max. V is equal to question mark. We don't know. That's what I'm asking. How fast is it going? And x is equal to 0. X is equal to 0.25 meters, like that. Okay? And, the energy is still the same as above. So we can plug in that energy. And we'll know all the other quantities in here except for V. And we can solve for that. All right? So let me cut and paste that solution. Okay, so what did I do? Here, this number right here, that's your E, okay, is equal to 1/2. M was 3.5 kilograms, okay. V we don't know, but that's what I'm asking for, how fast, okay. 1/2, K was 15, and X, we're not at maximum displacement now, we're at 0.25 meters, so 0.25 squared, and just working that through, that comes out to this number, which is 1.01 meters per second. Okay, so that's how fast it would be going. Now, um, you could say, does that number make sense? Well, compared to Vmax, the maximum velocity is going to be 1.44, and it's less than Vmax, so yeah, it makes sense. Okay, so think about it this way. My extended finger here is equilibrium. When you're out here at the 55 centimeter, 0.55 meters, it stopped. Velocity is 0. But then it starts to move towards the middle. Okay, and as it moves towards the middle, it goes faster, 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 faster. Right at the middle, it's reached 1.44 meters per second. Okay, well, if you're out here, you're not at 0. So not all the way out at the end, but somewhere in between. You're not at 0. You're not at the 1.44. You're a little bit less. You're between 0 and 1.44, and 1.01. It's within the right limits. Okay, so you should check your numbers, or think about the answer that you got, make sure that it makes sense. If you had done this problem and for some reason you came up with v equals 3, you should say, wait a sec, how can I get a velocity of 3 if my maximum is 1.14? And so yeah, you would have noticed that there's something wrong. Okay, so there you go. There's a quick example of harmonic oscillator problem. Okay, so with Monday's class and this one, I've reviewed everything that's on the test. Okay, so if there are no questions, we're done. Let me take a look here in the live stream. Okay, so we've had 2 dedicated viewers throughout. That's all right. I mean, 2 viewers is better than 0, I guess. All right, if there are no questions, let me just type it in the chat here. If there are no questions, then we're done. I'll wait just a second here to see if anyone has any questions. All right, doesn't look like it. Let me just say goodbye. And, if you have any questions, then catch me during my